And let us quickly start without wasting any more time. So today I will introduce you to machine learning, and mostly we look at the basic algorithms and models of supervised and unsupervised learning. And as usual, if you have any questions, I will address at the end of the lecture. And as I mentioned, we can also have a separate session only to address questions on today's lecture. And as I told that we need some uh, basic background on differential calculus, but I will explain wherever we are using the mathematical terminologies. So we will start with talking about the difference of supervised and unsupervised learning, and under supervised learning we'll look at classification using decision tree. Then we look at linear regression, a particular model called gradient descent, which is we'll use in the next example when we'll talk about neural network, or to be more precise, we will talk about feed forward neural network. There will be other types of neural network. One such is convolutional neural network, which we will look at in a later lecture. But today we'll talk about backpropagation algorithm, where we will use some concept of the gradient descent we discussed earlier. Then time permits, we will talk about clustering, and under clustering we'll talk about k-means and K-medoid algorithms, which are type of partitioning clustering algorithm. Then we'll talk about hierarchical clustering algorithm. We'll spend one slide on cluster validation index, but as I told before that later on we will have a separate lecture on machine learning model validation. And then, as like our previous lectures, we will have two IUI case studies. Although in the later lecture, as I mentioned, that in multimodal human-robot interaction lecture or automotive and aviation user interface lectures, you will find more case studies on machine learning for developing intelligent user interface. So supervised learning, we can term it as classification, also regression, and here it is supervised. That means we need a set of training data, and using this training data we train a model, and then we test it on a test data set. And in unsupervised learning we do not have training data, rather we describe our data through a set of features, and let the algorithm itself to either partition these data points into different clusters, or divide and combine them, as we will see in the hierarchical clusters. And the output from supervised learning is either as assignment of elements into classes, and similarly from clustering also we will get assignment to different clusters. There is the third kind of learning, is the reinforcement learning, which is somewhere in between, in which we will have something like a training data, or something we should say more like an experience. And instead of giving direct output to the agent, that whether it is correct or wrong, we give some sort of reward. So in CC, as you know, there are separate courses are already running on the reinforcement learning. And in today's lecture, we'll not look at the reinforcement learning, but maybe in a later lecture, we will look at Markov decision process and reinforcement learning. So what is classification and regression? So in regression, we predict a value from a set of input value, and in classification, based on this output value, we classify data points into a set of specific classes. So let us see some application areas like credit approval, target marketing, medical diagnosis. All are typical applications of classification. And also we can use classification for prediction. That means, say when I have an unknown data set, we predict its class, and based on the accuracy of the prediction, we evaluate performance of machine learning model, very similar to this information retrieval model evaluation that we discussed in the last lecture, using this confusion matrix and precision recall and F1 score. While in regression, we predict unknown or missing values, and there also we define a error function that we will see in a second and use it for evaluate a regression model. So first, we will look at a particular example of credit approval, and we will use decision tree for that. So here our problem is that we know certain parameters about a person, for example, his age or range of age, his income level, and his earlier credit history maybe. And using that, we will decide that what is the credit rating of the person. And this credit rating will be used to decide that whether the person is eligible for a loan or the amount of loan and so on. So similar analysis, all banking institutions or financial institutions, they use it very regularly to evaluate credit rating of person and deciding loan amount or credit amount and so on. So in classification, we will have two steps. In the first step, we will train a model. That means we will use a set of data in which we already know the result. That means we know all the properties like age range, credit rating, income level, etc. And we already know that what is the credit rating. So this is called the training data set, in which we already know the class of the data points. And then with that, we will train a model. So this model may be many different types. Like here we will talk about decision tree. It may be also a neural network model or maybe support vector machine, whatever. So irrespective of the model, then we will have another set of data, in which case we do not know the credit rating or we do not know the class, and those are called test samples, and we will use this to evaluate the accuracy of the model. So for example, see here is again another example, slightly away from the credit rating example, that it's we have a bunch of professors and we have their ranks like assistant professor, associate professor, full professor, the years they are working, and the prediction is whether they are tenured or not. And here we can see that we can do the classification based on a very simple rule, that based on their rank, whether the rank is professor and whether the years or the years are greater than 6. If one of these condition is fulfilled, then the person is tenured. So this is a very simple rule-based system or rule-based modeling. So here my model is just this if loop. And then if I have some test data set, like here Tom, Melissa, in their case, um, we can apply our rule and see that what is the accuracy of my previous model, which was telling that if professor or tenure is more than 6 years, then it will be tenured. So in case of Melissa, we think that this rule is not applying because Melissa is neither a prof, but she is working more than 6 years. But according to my previous rule, she should be tenured. But in this particular case, she is not tenured. That means the accuracy of my rule is for this 4 data set is 75%. That it is working for 3 of the samples, not all. And then we can use it for an unknown sample, say for example Jeff, who is a professor and working for 4 years, and we can predict using the rule that whether he is tenured or not. So this is the very basic notion of classification, that I will have a model and I will send that set of test data and see the accuracy, and once the model is accurate enough, we will use it to predict the result for unknown data set. So what is the decision tree? So remember we talked about tree and graph when we are talking about this breadth first search and depth first search, A-star search, etc. So again, we will come back to this tree structure. So here decision tree is a flowchart like tree structure, and each internal node denotes a test on an attribute and branch represent the outcome of the test. And there are two steps. One is the tree construction. That means at the first we have to construct the tree. That means we have to look at the rules and make the node, and based on the rule outcome, we have to assign values. And then it is also possible to prune the tree. That means the branches which reflect noise or outliers, that we will remove, and that will improve the accuracy of the decision tree. So here is our previous another example. that I know the age of a person, the income, whether he or she is a student or not. Also, we know the credit rating, and from that, I want to predict that whether the person is buying, will buy a computer or not buy a computer. And you can see that all of them have a specific set of values. That age can be less than 30, between 30 and 40, and then greater than 40. Income can be high, medium, low. Student only has two values, yes and no, and credit rating also have two values, fair and excellent. So this is a sample case of decision tree. So this is how the decision tree is looks like. That first we compare age. If it we check it whether it is less than 30, between 30 and 40, or greater than 40. And what we noted that for everyone in my this particular training data set, there are three samples, the third row, and then the penultimate row and the row before, and then there is another row in the middle. For these four rows, all answers are yes. So in my decision tree, if the age is between 30 and 40, I do not need to do any other check. And for greater than 40, I am checking the credit rating. If it is excellent, then I am saying no. If it is fair, I am saying yes. And similarly, for less than 30, I'm checking whether they are student or not. If yes, then they are buying computer. If no, no. So this looks pretty simple. But then you may ask that why I am testing the age attribute first. In this particular example, the age is happen to be the first column, but that may not also be the case. So there are specific algorithms to select the first attribute of choice, and that also dictates that how what will be the branching factor of the tree, so, or and what will be the depth of the tree, right? So here you can see that we have only two tests we have to do on every data point. On the other hand, if we first take the student attribute, it may not be the case, right? So there are ways based on the notion of information theory that how much variance there in each set of data, and that's how we can choose that which attribute we will compare first, and based on that we can select our first attribute. But it is also equally correct that if we can start the tree with student or income, there also we can draw the decision tree using the decision tree algorithm, and we can get also similar result. So in summary, what decision tree is doing, that here you can see that my training data set has a specific set of values. They are not continuous variables. And I am doing classification. That means I am assigning them into one of two class, like whether they are buying computer or not, whether they are tenured or not, or and whether someone's credit rating is good or not. So from classification, now we will look at another example of supervised learning, which is linear regression. So in linear regression, what we do, that we have a set of data points, and I just have to fit a straight line into that. So for example, you can think in terms of Microsoft Excel, that you have say X and Y columns of data. You are doing a scatter plot, then you are right clicking and you are adding a linear trend line. So the process looks very simple, but how Excel is drawing that linear trend line. So here I am using this particular website, which I find pretty good in explanation. So you may also look at the web page, and the good thing is they have also discussed the basics of differential calculus before going into the detail. So here we have a set of xy points, but remember that it is not only applicable for xy, so I can have x1, x2, x3, and many such column, and instead of a straight line I can also plot a plane or hyperplane. The algorithm remains more or less same, as you can see, but we will use only one input and one output because it is easy to visualize. And just for reminding you the equation of a straight line. So the equation of straight line is y equal to mx plus c. M is known as slope. Here you can see that change in y divided by change in x. and C or B, here it is written B, is known as the intercept. That means where the line is cutting the y-axis. And when I will develop a linear regression or for any machine learning model, I will predict an output and there will be an actual output. So in the previous example, predicted output was yes or no, and actual output was also yes and no. So for testing accuracy, I have to do the confusion matrix or this false positive, false negative that we were discussing during the information retrieval node. But in this case, since these are continuous variable, so we can define some function between the actual and predicted output. So here, the whole gradient descent or linear regression fitting algorithm works based on an error function. Error is the difference between the predicted and actual. And as a data scientist, we will try to reduce this error. And we will test with different slope and intercept of a line and try to see that where the error is reduced. So the error is defined as a cost function. So here you can find the definition of cost and loss function. So loss function computes the error for a single training example where cost function is accumulates them. And to get rid of this negation, that means y can be both greater than or less than y dash, but we should treat them equally, as you can see in the top graph. So we square them and add the square of them, and it's very much similar to this root mean square. So you can also take the root of the cost function as your objective function or your loss function. So that is also fine. So here we will go with the square function, and we are squaring to treat both positive and negative errors equally. So here we will just discuss some quick definitions or how we are going to minimize the error function. So what we will do that imagine that I have a set of points and I do not know that which straight line will fit into them. So I will take an arbitrary straight line, and how I will define a straight line by this equation y equal to mx plus b. M is the slope, b is the intercept. Next, what I will do, I will change very small amount of value in m, which I am signifying by del m. And similarly, I will change small amount of b by del b and see that how it is altering the cost function. So here we are showing that how we are trying to minimize that. So if you remember our differential calculus, so whenever we have a function and we are trying to minimize that, we take the first derivative. What the first derivative means? First derivative is nothing but the tangent. And what is the second derivative? Second derivative is curvature of the curve. So, or a metric of curvature. So when we are taking the first derivative, we are drawing the tangent, and in the whole gradient descent, what we will try that we will keep on changing so that the uh, tangent becomes parallel to the x-axis. That means the differentiation of the function becomes equal to 0, and the del m and del b, these changes will be such that we are as if we are descending down this curve so that the gradient becomes 0, and thus the name comes that gradient descent, that we are descending continuously. And later we will see that that is also one of the main problem of gradient descent algorithm, because we always try to minimize it. And if you remember that when we are talking about state space search, we did mention about some term called local optima and global optima, and in simulated annealing and genetic algorithm, we talked about a random function. So I am mentioning all this to convince you the fact that the basic idea of AI, this gradient descent or minimizing loss function, is more or less same across all algorithms. But let us come back to our case here. So here we are reducing here this is the straight line equation y equal to mx plus c, or here the intercept is marked as b. Next, what we will do that the error function, this is a uh, function of both the slope and the intercept. So in the previous slide, as you can see, that I can replace the y with the straight line equation, which is mx plus b. So I am just defining this error function as a function of slope and intercept. And what I will do is I will partially differentiate them with respect to m, and I will partially differentiate it with respect to b. We will equalize it to 0, and that way I will keep on change the slope and intercept. So if I take the derivative with respect to m, it becomes according to our formula that 2 into error, like x squared derivative is 2x. So same formula, 2 into error into del m error, and del j del b is 2 into error into del b error. So next, I do not know this term del m error, so we will find that. So here you can see that in the place of y dashed, I am putting mx plus b, because m and b, this is my model parameters. And then I am differentiating it. So here x is given value because x is already given to me. I'm trying to predict y, as do b and y. These are also constant with respect to m. So the del m error is simply x. And similarly, del b of the error is here, both m, x, and y are constant with respect to b. So del b is equal to 1, right? So I am just putting this value in this equation. So what is del j del m? J is the error function, is 2 into error into x, while del j del b is 2 into error into 1, which happens to be 2 into error. So just that is written in the other next slide, that del j del m is 2 into error into x, and del g b is equal to 2 into error. And then I am multiplying it by a learning rate. So this is something I am incorporating myself. This is not coming from the equation. So this learning rate decides that how fast I am reducing this function, and it decides both the convergence of the algorithm, that how quickly it will converge. So remember last week when we were talking about PageRank, we are telling that it has been found that PageRank converges in 52 iterations or etc. So this learning rate decides that, and there are pros and cons of using a big learning rate and small learning rate. So the if I use a very big learning rate, then I can miss the optima, and the algorithm can go into loop. That means it fails to reach the minimal point. And if I use a too small learning rate, then the algorithm may need too many number of iterations to converge. And there is no hard and fast rule to choose the learning rate. Perhaps we can start with 0.5, and then we can experiment based on our particular example or data set by slightly increasing and decreasing, that where we are getting good performance. And finally, what we do, that we decide the new m in the next iteration by by changing the previous value by this error into x into learning rate, and the same way we change the value of p, and we can uh, keep on changing b. And same way we keep the algorithm iterating till it converges to a point where either there are many conditions of stopping the iteration. Say for example, I can pre-decide number of iterations. Like in one example I was talking, that you will see that there are 5,000 iterations. In another case, I can define a minimal value of error, that what is the uh, where I will reach this minimal tolerance level of the error. Those can be the stopping condition. So from linear regression, now we will move to neural network, and you will see that it is very similar to linear regression. So a single neuron, this is simply doing a linear regression. So here you can see that I have a single neuron, and there are two functions. One is sigma, another is drawn like a step function. So this sigma function is simply doing the linear regression. So a neuron has inputs. So in this particular case, again, I am using two input, but it may have multiple units. And these inputs are associated with weights, and these weights are my model parameter. As in my previous example, the m and b, That means slope and intercept was my model parameter, and I was differentiating with respect to M and B to minimize the error factor. In neural network, W1 and W2 are the model parameters, and the sigma function is just multiplying x1 W1 and x2 W2. So in this particular case, we pre-choose some values of 0.5, 0.5, and zero point 0.3 as x1 and x2 as 0.8, and then I am getting 0.55 as a sigma function. And this step function, it has multiple purpose. That this step function can work as a classification example. That means if the value is more than 0.5, I will output 1, otherwise 0. And it can also sometimes work as a limiter. That means so that the total summation doesn't exceed a particular pre-chosen value. So for example, say I am using a single neuron as a network. So there is no neural network, there is a single neuron. And I am trying to train this function that the step function is fx equal to 0 when x is less than 0.5 and fx equal to 1 when x is greater than 0.5. So in this particular case, since the value is 0.55, so y equal to will be 1. If for another input value x equal to 0.45, then fx equal to 0. So up to that, this is simple. And this way I can use a single neuron without any neural network as a classifier as well as a regression example. So next we will talk about a concept called activation. So the activation function, it limits the amplitude of the neural output, and the adder function is just multiplying the weight with the input. So then why we do need neural network? Because as we see that with a single neuron, I can also do binary classification and we can do linear regression. So if you slightly remember something on the digital logic, so remember we have taught about some function called OR function, AND function, XOR function like that. So OR function tells that X or Y, that means if X, either of X or Y is 1, then the output will be 1. And if both X and Y are 0, then the output will be 0. X and Y is just opposite. If both X and Y are 1, then the output will be 1. If any of X and Y equal is 0, then the output will be 0. And XOR function is if either of X or Y is 1, then the output will be 1. If X and Y are equal, that means if both are 0 or both are 1, then the output will be 0. So in this particular picture, this gray means that this is 1 and the black means that these are 0. So in the first case, I can draw a straight line which is separating the grays from the black. And in the second case also, I can draw a straight line which is separating the grays from the black. But in the third case, I cannot draw a straight line separating the blacks from the gray. And this particular principle is known as linear separability. That means when two when I cannot draw a straight line to distinguish among different classes. And that's why when, or similarly in regression, when I cannot fit a curve, which is a straight line, that means I need a polynomial curve, then we cannot work with a single neuron. Rather, we have to go to a neural network. So here is the very basic structure of a feed-forward neural network, that there are input nodes, and then these nodes are connected to another set of nodes, and these black nodes are known as hidden nodes. And it has 3 layers of nodes, as you can see. That one layer of first layer is input nodes, which takes input. Then there is a layer of hidden nodes, which takes input from the input nodes and feed the values to the output nodes. And the output nodes output classes. Or we can also combine them to get a continuous value, as we will see in the next example. So then we can also use a neural network as a regression model, right? And all these links, they have a weight associated with them. So we can just define the input layer as the ith layer, the hidden nodes as jth layer, and the output nodes as the kth layer. And that's then we can number this node weights as wij or wjk. So we will go to see an actual example very shortly. So the inputs are fed simultaneously into the input layer, and all of these new neurons, they behave similarly, and the weighted outputs of these units are fed into hidden layer, and the weighted outputs of the last hidden layer are input to units making up the output layer. So the units in the hidden layers and output layer sometimes also referred to as neurodes. And if a neural network can have multiple hidden layers, so there is some sort of rule of thumb, although I am not very sure about this, that if your neural network has more than 4 hidden layers, then we can term it as a deep neural network. And the specific example, as I mentioned earlier in the lecture also, it's an example of feed forward neural network. Also there are other type of neural network, for example radial basis network, and we will also look at convolutional neural network later on, which has slightly different structure. So next we will look at that in case of linear regression, we saw that how we can use the gradient descent algorithm to change the m and b, or the slope or intercept of the straight line based on the input data sample. So a very similar algorithm here we will use, which is known as the backpropagation algorithm, and the principle you will see the exactly same as gradient descent. That means we will calculate a error function, and then I will differentiate or partially differentiate with respect to the weights of the links, and then I will find the del w, that means change in the weight, and we will adjust the weight, and we'll keep on doing that. So the basic principle of backpropagation algorithm. So this backpropagation algorithm is used to train neural network. So imagine that as like the decision tree example, that I have a training data set where I know the actual class or actual values for a regression example, and I will feed this data to the neural network, and then I will adjust the weights so that for an unknown example, it can generate the actual class. So here is an example. I again take this example from the website, which you can see below, and I like this particular example. So here I1, I2 are the input node, and also there is this bias node B1 and B2. You can treat it just like another input node, but although it's the input is not going to all the uh, nodes, it's not going to the input nodes, it's only going to the hidden and output nodes. But it will be treated very similarly like the all the other nodes. Okay. So here is the structure I1 and I2. These are the value 0.05 and 0.1. And my desired output is 0.01 and 0.99 for this specific set of input. So for this particular model, I want that when my I1 is 0.05 and I2 is 0.1, the output 1 will be 0.1 and output 2 will be 0.99. So how we are proceeding in the backpropagation algorithm? So backpropagation algorithm works in 2 stages. One first stage is called the forward pass, when we move from I1 to H1 to O1. That means in this direction, left to right. And then we have a backward pass. In backward pass, we come from right to left, and we update all the weights so that I get my desired output. So for example, here I am trying to find the input to H1, and all these red colored values for weights, these are, you assume that these are randomly selected. So I have to initialize all weight with certain values, and we can choose random values to initialize the weight. So these are my initial values. And here B1 and B2 are the bias nodes. Their values have 1 and they will not change. Right. So net H1, that means what is coming to H1. So see W1 into I1. So this W1 into I1. So 0.15 into 0.05. Sorry, I think I moved. Yeah. W1 into I1, 0.15 into 0.05 plus W2 into I2 here, zero point 0.2 into 0.1, I2 into W2 plus B1 into 1. B1 into 1. B1 is 0.35, this connection. Okay. So a H1 has 3 links, incoming links, W1, W2, and B1. and I am just simply multiplying that, and this is net H1. And then we are using a logistic function. So in the previous example, you may remember that for a single neuron, we also have this step function. So instead of step function, we can also use a logistic function. So the equation looks a bit complicated, that 1 by 1 plus e to the power minus x. But the calculation is pretty simple with a calculator. So the output of H1 will be 1 plus 1 by 1 plus e to the power minus net H1, which turns out to be this value. And similarly for H2, we can first multiply W3 into I1, then W4 into I2 plus 1 into B1, right? So that will be net H2. And then I can put this equation 1 plus 1 by 1 plus e to the power minus net H2, and I can get this value. So that will be the output from H1 and H2. And exactly similarly, we will calculate the output of 1 and O2. So O1 will be zero point 0.4 into net H1 plus 0.45 into net H2 plus 1 into B2. And similarly, O2 input will be W6 into H1 plus W8 into H2 plus 1 into B2. So following the same calculation, it is very, as you can see, it's very repetitive. That's why we use computer program for doing that. And in the last mail, you can already find that I shared a backpropagation source code example. So following that, we get the value of output O1 and output O2. But see, this is wrong. Why? Because I want O1 as 0.01 and O2 as 0.99. But instead I am getting output O1 as 0.75 and O2 is 0.77. That means the neural network is not yet trained. So I have to adjust the weight accordingly. How we will adjust the weight? So there comes the backward pass. That means right to left pass. So here we will again use the very similar concept as in the gradient descent example. You can see we have the exactly same formula for error function, half target minus output square. So here we calculate it to be 0.27 for output 1, and O2 is similarly 0.023, and the total error in the network's prediction is we just add these two values, right? Next, what we will do, that we will differentiate this error with respect to individual weight. So this is a zoom in of the output node O1 here, right? So here how I am calculating output O1, that W5 into H1, W6 into H2 into B2 into 1. And then I am using this 1 by 1 plus e to the power this complicated function. So I will differentiate the total error with respect to W5 to adjust W5. Very similar, like we differentiate the total error in the gradient descent example with respect to M and B. So I will use the product rule because E total doesn't directly depend on W5. So daily total is depends on output of O1, then output of O1. So here the error is here. So it is a function of output of O1. So I am differentiating with respect to that. Output of O1 is a function of net O1, which is by this multiplication. And the net of O1 is a function of W5. So this is the product rule of differentiation. And then what we will do, that we will calculate all of these values individually and multiply them. So for example, this is the function of the total error, and I am partially differentiating it with respect to output of 1. So the whole this half target O2 minus output O2, this is a constant in this case and is not contributing anything to the partial differentiation. And now I am using very similar in the previous case, that differentiation of x square is 2x. So that's why I'm using the half also before. 2 into half target 1 into minus out O1 into minus 1. So minus out O1 differentiation with respect to out 1 is minus 1 plus 0. So the daily total by del out O1 is we can put this value. And similarly, this is the function out1 is 1 by 1 plus e to the power minus net1. So similarly, I can calculate the differentiation of del out1 with respect to del net input to o1, and this is the differentiation, and I can put this value. And finally, how much we can differentiate net 1 with respect to W5, del W5, and this is the formula of net 1, which is if you see in this, the W5 into H1, W6 into H2, 1 into B2. So W6 into out H2 and B2 into 1, these are constant in this case. So net O1 differentiation with respect to del W5 is 1 into out H1, which is equal to only out of H1, and I know this value. So putting all together, daily total del W5, this is the multiplication. I can multiply all these three values that I calculated, and we will modify the new W5 by this value. That earlier W5 was 0.4. If you see here, W5 was 0.4, and then I will modify W4 by daily total del W5, and just like the learning rate, I am introducing this eta here, which is the learning rate, and this I can choose based on my uh, choice. So generally we use it 0.5 to begin with. So I will 0.4 minus 0.5 into this value. And next we have to do this for all weights. That means we have to do it for W6 very similarly, then W7, W8, and then we have to backpropagate and do the same calculation for W4, W3, W2, and W1. And we will modify all these weights accordingly. And then we will rerun this whole exercise again. So that will be my second iteration. And again, I will take all these value and keep on modifying this weight. So this way, these algorithms will iterate between forward and backward pass, and we will keep on adjusting the weights unless we are meeting the stopping criteria. And it's same as I discussed in the previous case, that a minimal error or a standard predefined number of iterations, all we can choose. So this is the backward pass, as we discussed, that we have to do it for from the we have to do the repeat the same thing for the hidden layer, and then we have to propagate it back into the input layer or W1. And this is one example of the source code. So let me see if I can run it. So if you, I am not sure if team is, can someone confirm that if you can see a second window on the top of my slide?
Yes, sir.
So I am now loading a text file. So if you can you see it? Although I already shared it with you, so even if you do not see it, you can run it uh, yourself. I am just running the exe here, and I am also not sure whether a team will be recording it. So let's not uh, spend too much time on this particular one. Sorry, just once. So here what I am trying to do is I am running a software which execute this uh, backpropagation algorithm, and now I am trying to load a particular data set, and then we can show you the running of backpropagation in the form of straight line fitting. So I am not sure that if it's being recorded. So anyway, I will stop it. So in the particular example picture, you can see that these are the x and y, and these red dots are the data points, and the blue is line is fitted through it, and the learning rate is 0.1, and sigmoid alpha value is the spread of the 1 plus 1 by 1 plus e to the power minus function. That means how uh, I mean how wide will be the logistic function. And we can also choose the neurons in the first layer, which is the hidden layer, and we can choose the iterations, and it will output iteration and error. But this is a very basic example. But what you can do is that you can build your software code on top of that using a very basic neural network. And we already in lab we can add another input layer to it, and we can also change the neural function parameters into it. So it's a good starting kit if you are interested to do some coding on neural network. So next we will look at that how to. So we discussed about three different supervised learning model, the decision tree, linear regression, and neural network, and how to validate them. So we take our entire data set. One procedure is called cross validation. So more specifically tenfold cross validation, in which we divide our data set into 10 set. We use the 9 for training the model and test it on the remaining data set, and repeat this procedure 10 times. And when we are dividing it into 10 set, we do it randomly. But in that context, we also use a concept called load balancing. Load balancing means that we should have nearly equal number of samples for each class or each range of the output variable. So we will not discuss it detail it here, but we'll have a separate lecture on model validation. And another technique, in which case to say we are collected data from a small number of samples, because we are talking about intelligent user interface development. Many times our results come from user studies where we do not have, say, 10,000 data. So in those cases, what we can do, we use a technique called leave one out validation. So say we can uh, train the model with all participants data except one, and then we test the model on the remaining one, and then we repeat this procedure for all remaining participants. So that is called leave one out validation. So next we will quickly go through a couple of examples of using uh, a couple of examples of using a very basic neural network, not the convolutional neural network or deep neural network. So the one example is classification for target prediction. So here we, from the domain of AI, will move slightly towards the human computer interaction domain. So all of us use mouse pointers in screen, in laptops, desktop computers. So if from earlier studies, ranging from 1899, uh, it has been found that this pointing movement, they can be modeled as a typical type of movement called rapid aiming movement. And the rapid aiming movement is like the movement when you are trying to catch a ball or type a key. And it has two distinct phases. One is called ballistic phase, another is called homing phase. That means once I am moving the pointer towards the target or toward an icon, and then I am trying to stop the movement and home on the particular icon. So that is called homing phase. And since we were working with many different type of interactive devices like gesture control, eye gaze control, etc., we try to detect this homing phase from the cursor trajectory. That means speed, acceleration, bearing of the cursor movement. And then we use neural networks to determine that when a person is trying to stop cursor movement, as opposed to taking it towards the target. So for example, you have a whole set of icons on your screen. So it may be that you are trying to hit the topmost top left corner icon. So your icon will cut through a bunch of icons. So when it is cutting through, it will have quite high speed. But when it is nearing the intended target, then you will slow down the speed. So the concept is that I'm trying to find out that when you are slowing down the cursor speed to select the icon, and it has special significant when we are working with people with the motor impairment because they have trouble in stopping cursor movement. And here we trained a bunch of models with the cursor trajectory metrics like speed, bearing, and acceleration. And a neural network model worked best. This is a very simple example of a backpropagation neural network example where we are feeding the velocity and bearing angle of the cursor movement, and we are trying to predict phase of movement. And this happens to be the algorithm. So basically, we are measuring the speed, bearing angle, and acceleration of the cursor movement. We are feeding to a very single layer feed forward neural network, and the neural network works like a binary classifier. And when it is predicting that the user is trying to stop the movement, we predict the nearest target as the current intended target. And then we evaluated with respect to three criteria like availability, accuracy, sensitivity. So let's not go into detail on this evaluation. And it turns out to be that the neural network worked better than the other models, and we evaluated it for different pointing devices. So rather, we can look at a demonstration. So here you will see that there are two pictures of similar to the multifunction displays used in fighter aircrafts, and it is designed according to a specific model. And here, what you will see that I am wearing a emotive EEG headset. I am not using the EEG for the time being, but using it as a head movement tracking technology. And we also have a eye tracker below here attached to the screen. So I can switch between both these modalities, eye tracking or head tracking. And when I am holding a cardboard plank in front of the eye tracker, then the eye tracker automatically gets cut off, and I can move the cursor with my head movement. And as you can see in the screen, one of the blue uh, icon turns uh, white based on the predicted movement. So when the cursor is moving very fast, none of the blue buttons turns white. But when it is slowing down, then one of the blue button turns white. So now I am moving the cursor based on my head movement. And next we can switch back to eye gaze movement. So this is one type of multimodal interaction that precedence based technique, that one of the interaction device got precedence. Here eye tracker has precedence. So when eye gaze movement is available, I can move cursor with eye gaze, and when it is not available, I can switch to head tracking. And with both of the technology, this target prediction algorithm is installed. So the second example is our gaze controlled hard or HMD. I think on the very first lecture, I show you some demonstration. So here is the underlying technology. So our main challenge was that we are trying to track eye gaze on a windshield of a car, and the windshield is not flat, or rather it is kind of curved. And the eye tracker was quite far away from the windshield because it cannot track eye gaze when it is more than 2 feet away from the eye. So what we did is we compared performance of a linear regression model and a neural network model, and we compared the R square and RMS values. And from that comparison, we chose a neural network model, and we find that the mapping between coordinate spaces of the eye gaze tracker and the windshield, they are not linear, rather they are polynomial due to the curved nature of the windshield. And we develop this algorithm by which we take the XY eye gaze coordinates from the eye gaze tracker, feed it through a neural network, and convert it into another set of XY coordinates, which we use to activate targets on the windshield. So this is one example we recorded in a Toyota car, and you already seen it in the first lecture. So now she's playing, and she's pointing images, but selecting using the wireless mouse attached to the steering wheel. Extract and detection feature. Now she is selecting another button, and we evaluated it with a standard pointing task. And this is in low light condition. So anyway, I think you got the idea, and these are the timing parameters recorded for this particular user interface. And then we use the similar concept of mapping instead of a screen-based eye tracker for a head-mounted eye tracker. And again, we compare the R-square values and RMS error and use it to track eye gaze for a large screen display, which is a representative of a head-mounted. So here also the eye gaze tracking glass give us a XY coordinate. We feed it to a, again, very simple backpropagation neural network like the one we just discussed, and it converts the XY coordinates into another set of XY coordinate, which we use to draw a cursor in this large screen, which is far away from his head. And similarly, we can map this XY coordinate to any plane, both flat and curvilinear, using this similar neural network. So here we are mapping it to a near display, while we can also map it to a far display. And these are studies undertaken at our lab, and we found that compared to the existing interactive device, this eye tracking device is reduce pointing and selection time almost by 1/3. And presently, we are still working on this system to integrate it with the actual display system. So with that, now we will enter the last section of our talk, which is the unsupervised learning or cluster analysis. So as opposed to supervised learning, here we do not have any training data set. So for example, in this picture, as you can see that we have three different colors of objects, red, green, yellow, and blue. And we are grouping objects based on their feature. And in the upcoming slides, we will just use uh, two feature or three feature for ease of visualizing, but the same algorithm, you can do it for multiple features. So the output of cluster algorithms are clusters, and the cluster algorithm works based on two types of distance measurement. One is the intra-cluster distance. That means the distance between individual data points. So here all these red, yellow, or blue circles are my data points, and we try to reduce the distance among the data points inside a single cluster. And then there is another type of measurement which is called intercluster distance, and we try to maximize it. So here uh, we are, for intracluster distance we are trying to minimize, for intercluster distance we want to maximize. So well, this is the formal definitions of cluster analysis, and often the cluster analysis is used as a pre-processing step for other algorithms. Even we can sometimes use cluster analysis as a pre-processing step of a classification algorithm. And it group data objects into cluster, and each cluster is defined by a cluster center. And these are the example like pattern recognition, image processing, bioinformatics, and information retrieval, where we can use cluster techniques to for document classification. That means when I do not know the we do not know the class of documents, we can use cluster analysis as a pre-processing step of a classification example, that we can automatically cluster document, and the cluster center we can use as classification or classes. So there are two types of distance metrics. So how we are going to measure the intracluster or intercluster distance? One, the most basic one is called the Minkowski distance, which is the xi1 minus xj1 to the power p, and it is looking complicated. But if you put p equal to 2, then it becomes very well known Euclidean distance, which we mostly used. And if I keep p equal to 1, then it becomes the Manhattan or city block distance. Most commonly, we use p equal to 2 or the Euclidean distance between data points, right? And these are the major clustering approaches. So here today we will talk about partitioning and hierarchical algorithms. So in the partitioning algorithms, we randomly partition data points and then assign data points to individual partition, and we iterate over these assignments until we are minimizing the intra-cluster distance and maximize the inter-cluster distance. Hierarchical clustering on the other way, that we do a hierarchical decomposition of the set of data. And then there are other clustering algorithms like density-based, grid-based, or model-based, which we will not, probably model-based we will briefly discuss today in one or two slides in the form of expectation maximization algorithm. So the basic concept of partitioning algorithms, and the most common one is K-means and K-medoids, that each cluster is represented by the center of the cluster. And how the K-means work, that it's very simple. We randomly select a predetermined number of cluster center. Here K stands for the number of clusters. So one question you may think about, that how do I know the value of K? Which is a very valid question, but for the time being, you assume that you already know the number of cluster. So then what I will do, that I will randomly select K number of points. I assign all data points which are nearest to my K cluster points, and I will recompute these centroids from these my assignments, and then I will repeat this procedure until the centroids do not change. And this algorithm is very simple, and the input is only K, or the number of clusters, but it has certain disadvantages. The disadvantages means that it can be proved that it only works on convex dataset. For example, if my data points are say standing like our in a single straight line, then K-means algorithm will not be a good candidate to cluster this point. And also the cluster centers, that will not be individual data points, but that will be calculated based on the values of the individual data points. Now that may be a problem. Say for example, in a class you are clustering students based on their marks on different subjects. Now after you do the cluster, you want to select cluster center, but then the cluster center values, you will find that since you are averaging all the values, you will find that you cannot assign the cluster center to an individual student, because these are synthetically calculated from the existing number of students. So, and also since we are averaging the values in calculating the centroid, there is a problem that it is very much dependent on outlier. That means say one point is very much away from other points. So it can wrongly assign the outlier as a single cluster center. So these are the formally limitations of K-means, that the size, density, and non-spherical shape, it cannot work, and also it is susceptible to outlier. So the outlier problem and this synthetic centroid problem, that means we do not have a real data point as a centroid. Those two problems has been solved in K-medoid clustering methods, in which case instead of using averaging value or averaging the individual data points or randomly initialize the cluster center, we rather select individual data points as cluster center, and we iteratively replace medoids by one of the non-medoids if it improves the total distance of the resulting cluster. But it doesn't scale well, the partitioning around medoids, it doesn't scale well for large data sets. And then Clarence, these are some other algorithms which has tried to improve the performance of K-medoid algorithms. And many times the performance of your clustering algorithm will depend on the initial selection of cluster center. So the initial selection can be completely randomized, or it can be based on the total range of data or distribution of data. So Next, we will briefly look at the hierarchical cluster algorithm, in which case that at each step we measure the intra-cluster and inter-cluster distance, and based on those two distance, we combine multiple data sets into a single cluster. And the result is known as dendrogram, or a type of a tree. You can see it will look more like tree, that if you move the screen, rotate the screen at 90-degree angle. So here is an example of dendrogram, that at each level, this on the top right corner, you can see the distribution of data points. And when I am measuring the intracluster distance, so first I am grouping A and B because these are most nearby. Then I am merging D and D because these are nearby. Then I am merging D and D with C because these three are nearby. And finally, I am merging all data points together. So if I cut across the horizontally, so I will get, say if I cut here, I will get three clusters, A, B, C, and D, E. So next, we will address the other problem in k-means and k-medoids, that we, in both of these algorithms, we need to know the value of k, or the number of cluster center a priori. But what happens when we do not know that? So then there are two clustering algorithms which are known as soft. So in the previous all clustering algorithm, the output is that each data point will be assigned to a individual cluster. But in soft clustering algorithm, we get soft cluster, that instead of a hard assignment to a cluster, I will get either a membership value or a probability value. That means a value between 0.1 of each data point to each cluster. So theoretically, a single data point can be in two different cluster with two different membership or probability values. So the fuzzy C means, it is works very similar to K means, that we start with a random set of data points, but instead of calculating and then we calculate cluster center at each iteration as in the K means, but instead of assigning the data points to individual cluster, we calculate a membership value of each data point on each cluster, and based on these membership values, we define an objective function and try to uh, maximize or minimize this objective function. And the output of fuzzy C means is return cluster centers and membership values for each data point to each cluster. And a more sophisticated algorithm is EM algorithm, or expectation maximization algorithm. So in fuzzy C means, we use a concept of membership value, which is not true sense in probability values. But in EM algorithm, we use probability value, and we imagine that uh, each cluster is represented by a probability distribution, and we try to find this probability distribution. So here is a lot of equation, and you need not to go into the detail of all this equation. But what you can remember, that EM has two steps, expectation and maximization. So in one step, we find the expected value. What is a mathematical expectation? Mathematical expectation is the probability into the actual value. So for example, in k-means, k-medoid, we measure this intercluster and intracluster distance. So here the expectation is somehow similar to the intercluster distance, that what is the um, expected value of all data points considering their probabilities of belonging to each cluster. And in the next M step, we try to find parameter of this individual probability distribution, which I am imagining that they are generating the data point. So you can think about that as if there are multiple Gaussian distribution. I do not know their mean and standard deviation, but I am assuming that all my data points are coming out of this individual Gaussian distribution. And in this algorithm, we try to find this mu and sigma of this individual Gaussian distribution, which constitute my data point. So in the other algorithms, I am finding the I am defining the clusters by a single point. So in case of K means, this point I am calculating by averaging the value of the all data points belonging to a cluster. In K-medoid, I am assigning one of the data point as my cluster center. In expectation maximization, I am defining the cluster center as a Gaussian distribution in terms of its mean and standard deviation. And finally, how do I know that how good is the cluster validity? So there are several index like external index, internal index, or relative index, and all of we again discuss it in detail on the model validation lecture. So we will just show you an example of one XB indexing. And remember that when you are why we are doing cluster validation, that say I am running the k-means algorithm of different values of k. So how do I know that which value of k is optimum? So if I look for the best, then say if I have n data points, so my best clustering will be n cluster. So where each data point belong to a single cluster. So, but of course we do not want that as a result. So what we practically do, that instead of a single value of k, we take a range of values of k, say 2 to 6 or 3 to 8, whatever, based on our example. And for each of these values, we calculate this cluster validation index. And this cluster validation index, we can define it based on entropy, like P log P, or sum of squared error, something like that. And uh, there are many different index. So here is one is XB index. And like on the right side, we are showing the curve. So here you can see it's up and down. And we try to see that when we are trying to minimize it, so this value, maybe the which correspond to 3 is the best value of my cluster. So like that, we select the best value of cluster. That's what will be the optimal number of cluster. So finally, this is the summary of our long lecture. So we talked about different classification and clustering technique like decision tree, neural network for classification, linear regression. We touched about the topic of cross validation, and we talked about hierarchical and k-means clustering. Also, we talked about the limitations of k-means clustering, and one solution is the k-medoid clustering. Another solution is the soft clustering, where we need not to pre-specify the I mean, hardly assign data points to individual clusters. So we can, each data point can belong to multiple clusters. So we talked about cluster validation index, in through which we can decide the best value of k. And we looked at two case studies of intelligent user interface development, mostly on predicting target for um, interactive devices like eye gaze and head movement tracking, and then mapping coordinates between two different sensor spaces. So with that, I will stop talking and thanks.